Okay, so we are starting our circles chapter. It's everything we need to know about circles we are learning in this chapter. So before we get started on any problems, let's just go through some basic definitions. Let's talk about what makes a circle so special. Does anybody know what makes a circle so special?
There's no side.
Yeah, there's no sides, right? So it's definitely not a polygon because it's one big curve. That's correct. And also, what makes a circle very special is, down here, let's go over here, is we have one center, we have one point that we call the center point. Then there's a whole bunch of points around that center point. And do you know anything about the relationship between that center point and any of the other points that are on that circle? It's all the same what? Distance, exactly. This is what makes a circle so special. The distance from the center point to any point on the rim of the circle is the same distance from the center point, which is pretty cool. Does anybody know what we call those segments? Does anybody remember from proofs what we call those segments from the center to the rim of the circle? Yeah? Radii. And what do we know? Back to proofs. What do we know about all radii? They are congruent. All radii are congruent. We had learned that back, I don't know, what chapter was that? 3? Back in chapter 3. All right. So we know by definition a circle is a set of all points in a plane that are a given distance from a given point in the plane. The given point is the center of the circle and the given distance is the radius. A segment that joins the center to a point on the circle is also called a radius. The plural of radius is radii, which we all know. All right, some more definitions. 2 or more coplanar circles with the same center are called concentric circles. Two circles are congruent if they have congruent radii. Why does that make sense that if two circles are congruent, if the length of their radii are congruent? Why does that make sense? Yeah, so isn't the radius basically deciding how wide the circle or how big the circle is going to be? If we have a short radius, won't we have a smaller circle? Versus if I have a really long radius, wouldn't I? Oh, that's a bit of an exaggeration. But if I have a longer radius, wouldn't my circle then be larger? Right, so it makes sense. If the radii are, the radius is deciding how big the circle is. So if the radii of two different circles are congruent, then those circles have to be congruent. All right, a point is considered inside or in the interior of a circle if its distance from the center is less than the radius. That makes sense. Right, in the diagram, other than the center point, aside from the center point, can somebody tell me which point is in the interior of the circle, aside from the center point? A. All right, O is also in the center, but I said interior, but I said aside from the center point. All right, a point is considered outside or in the exterior of a circle if its distance from the center is greater than the radius. Can somebody tell me the point that's considered in the exterior of the circle? The exterior. Amanda. C. And a point is considered on the circle if the distance from the center is equal to the radius. So which point here is on the rim of the circle? Ignore that point right there. We don't care about that point. Nora? B. All right, let's keep going. All right, some important definitions. We're going to talk about a chord of a circle. A chord of a circle is a segment joining any 2 points on the circle. When I say on the circle, I mean on the rim of the circle. And does anybody know what the most famous chord of a circle is? It's the most famous chord of a circle. Dimitri? The diameter. So a chord is basically a segment in the circle whose endpoints are on the rim. Well, a diameter definitely has its endpoints on the rim, but what makes a diameter more special than all the other chords? What makes the diameter more special than all the other chords? Good. A diameter also goes through the center. Okay, so a chord is a segment whose endpoints are on the circle. A diameter is a chord, but it has to go through the center. All right, radius chord relationships. The distance from the center of a circle to a chord is the measure of the perpendicular segment from the center to the chord. What do I mean when I say all of that? You don't have to draw this, you could just pay attention. So let's say I have circle O and I have chord AB. And I ask you, what is the distance from O to AB? What you would have to do is you would have to draw your own perpendicular. And whatever that length is, obviously I have to give you other information to be able to figure this out, but whatever that length is, that would be the distance from the center to the chord. It's the length of the perpendicular segment. So in this diagram right here, what would be the distance from center point O to chord AB? It would be the length of OP. All right, let's keep going. All right, so how can this be used? So even though we're done with triangles, triangles never really go away. So it says that AP is 9. The radius of circle O is 41. This is where we have to think strategically. Now, we know a radius is a segment from the center to the rim. Now, I can draw my radius like this, right, and say that's 41. That's not going to help me. Where do you think I'm going to draw my radius so it actually helps me? Joe? Good. We can either go OA or we can go OB. Okay, we can either go OA or OB. Why? Why can I either go OA or OB? Dimitri? Okay, but I can go like here and that's on the outer rim too. To create a triangle. So I can either go OA or I can go OB. Let's say I go both of them. Let's say I draw OA and I draw OB. I actually now have 3 triangles. I have the big triangle AOB, and then I have the 2 little ones, AOP and BOP. All right. Do we agree that OA and OB are congruent because all radii of a circle are congruent? Do we also agree that OP is reflexive? So these 2 triangles are congruent, not by side, or angle, side, side. Angle, side, side's not a way. What method are these 2 triangles congruent by? Omar? HL. These 2 triangles are congruent by hypotenuse leg. So my whole point in doing this is to show you, since these 2 triangles are congruent, if AP is 9, is BP also 9? Yeah, that was my whole point in doing this, to show you that this perpendicular also ended up bisecting. So now we said, let's just use one of these triangles. I'm using APO. They told us the radius is 41, so I'm going to label a 41 here. This is a triple that I hope you didn't forget. 9 something 41. Ethan? 40. So find the distance from the center to the chord. The distance from the center to the chord is 40 units. All right, let's keep going. All right, theorem. If a radius or part of a radius is perpendicular to a chord, then it bisects the chord. What does that mean? Basically, if I have a segment coming from the center of the circle, if that segment is perpendicular to it, it will also bisect it. And the reason is exactly what I had showed you up here, because you'll always be able to create two congruent triangles, which means those two bottom parts are congruent regardless. So that's why, exactly what I showed you in that last problem. So anytime you have a segment coming from the center of the circle, if it's perpendicular to the chord, it will also bisect the chord. All right, and the inverse of that is also true. If a radius or part of a radius bisects a chord that is not a diameter, then it is perpendicular to the chord. Right? And that's basically just telling us if I know that OD bisects AB, I can draw my radii and say those are congruent. And then I could say OE is reflexive. Then I can prove angle 1 and angle 2 are right angles. So I can CPCTC angle 1 and angle 2, so they're congruent. And then I could say they're supplements. And what do we know if two angles are congruent and they're supplements? They have to be right angles. So that's the flip side of this. So sum that whole thing up. If a segment from the center of the circle is perpendicular to a chord, it bisects the chord. If a segment from the center of the circle bisects a chord, it will also be perpendicular to the chord. How is this going to work for us? Let's see a problem. The radius of a circle O is 13 millimeters. The length of chord PQ is 10 millimeters. Find the distance from chord PQ to the center. All right. So the radius of circle O is 13. The length of chord PQ is 10. So I'm going to label it like this. PQ is 10. Where do you think I'm going to draw my radii to help me? Because I can draw so many radii in this diagram, but there's only specific locations that would help me. Ethan? Good. Why? Exactly. Even in circles, it always comes back to triangles. So even in the circles unit, it comes back to making triangles. So I'm going to go from O to Q and O to P, and I know the radius is 13, so PO is 13, OQ is 13. Now they want us to find the distance from the chord PQ to the center O. That was one of the first theorems we learned today, right? The distance from the center to the chord is the length of what? Distance from the center to the chord is the length of what? What should we draw? The distance from the center to the chord. A perpendicular segment, you got it. It is the length of the perpendicular segment. That's what we need to find. All right, but didn't we just learn if there's a segment coming from the center of the circle that's perpendicular to a chord, what does it do to the chord? It bisects it. So that 10 will get split into two fives. This is a triple, 5 something 13. What's that triple? AJ? 12. So find the distance from the chord PQ to center O. It is 12 units. Oh, sorry, 12 millimeters. All right, so in my opinion, number 2 would be a great assessment question. It'd be a great test or quiz question. Two intersecting circles have a common chord that has a length of 18. The radius of one circle is 15 and the other two is 40 and the other is 41. Find the distance between the centers of the two circles. All right, go back. We read through it once. Two intersecting circles have a common chord that has a length of 18. I need to draw that common chord. The way, anytime you have a common chord situation, question like this, you're always going to draw that common chord in the same location. Do you see how it sort of looks like a Venn diagram? You're going to draw that common chord in the intersection of the two circles. So I'm going to call this common chord AB. So here's A, here's B, and I'm going to write over here over to the side that AB equals 18. I'm not going to label my diagram now with it because I don't want to clutter my diagram. But I'm going to need that later on, so that's why I left it. All right, so it says the radius of one circle is 15 and the other is 41. It doesn't matter. It doesn't matter which circle you make have a radius of 15 and which one you make have a radius of 41. So I'm going to go to circle Q because it looks a little bit smaller, and I'm going to say that has a radius of 15. But now I need to draw my radii very strategically here because that's going to determine how I proceed with this problem. I'm going to draw my radius from Q to the common chord. So from Q to A and from Q to B. And I know that has a radius of 15. Now I'm going to go to the larger circle. And the larger circle has a radius of what? Any ideas? Go back to the problem. The larger circle has a radius of 41. Where do you think I'm going to draw the radii of the larger circle to be strategic? Draw it. AJ? You got it. I'm going to draw it actually to A and B. So I'm going to draw from A to P, which is 41, and from P to B, which is also 41. I've now created a quadrilateral. Does anybody know what shape, which quadrilateral this is? Kaylee? A rhombus has all sides congruent, so it can't be a rhombus. So here we have top two sides congruent, bottom two sides congruent. Will? A kite. We've just created a kite. Top two sides congruent, bottom two sides congruent. That is a kite. All right, so we're going to keep that in our minds. Now that I know this is a kite, what does that mean? I can use all the properties of a kite to help me. So it says, find the distance between the centers of the two circles. I obviously need to draw a segment. What segment am I drawing when it says find the distance between the two centers? So what segment do I need to draw that I'm trying to find? Joe? QP. And now, isn't QP a diagonal of the kite? Is AB also a diagonal of a kite? So what you need to remember that in a kite, the diagonals are perpendicular and the long diagonal QP will bisect the short diagonal AB. So when it says that AB, or that common chord, is 18, I'm now splitting it into 9 and 9. And then I got some triples going on here. We got 9 something 41. What's that missing side altogether? What is it? 9. Oh, wow, the enthusiasm is just too much. I can't even contain my excitement with how proud you're all making me. It is 9, 40, 41, right? The other side is a triple times 3. So it's not really a triple I made you memorize, but it's one of those times 3. Does anybody know? Nora? This is a 3, 4, 5 times 3. So what's the missing side? 12. Now that I know that this is 12 and this is 40, can I find the length of QP? Absolutely. QP will be 40 plus 12. So QP will equal 52 units long. right, last one in section 10.1. And then we go on to 10.2. All right, if the chord of a circle is 60, find the distance from the chord to the center. So, read it again. If the chord of a circle is 60, let's call this A, B, C. Which segment are they saying is 60? AC is 60. And they're saying find the distance from the chord to the center. What do I need to draw? Anytime they ask the distance from the center to a chord, I always have to draw the same thing. What do I need to draw? A perpendicular. You got it. So I'm going to go ahead and I'm going to draw my perpendicular. And when I draw this perpendicular, what happens to that 60? It gets split into 30 and 30. And what's the relationship between these two triangles? What's the relationship between the two triangles that I just created? They are what? Congruent. We have radii congruent, we have reflexive, right? And we have the right angle, hypotenuse leg. Since they're congruent, what happens to that 120-degree angle? It gets split into 60 and 60. There we go. All right, so let's call this point D. I'm gonna take one of these triangles. We have B, D, C. This is 60, this is 30, and DC is 30 units long. All right, so now we got to remember, opposite the 30 is x, opposite the 60 is x root 3, opposite the 90 is 2x. What is my equation to solve for x? What's my equation to solve for x here? Someone besides Joe, somebody else, have a thought, have some energy. Can't even blame it on the morning anymore. It's been a long day. In the morning, it's too early, and in the afternoon, it's been a long day. All right, I'll just call on somebody. Matt, tell me, what's the equation I'm going to use to solve for x? That's not a good answer. Take your AirPods out. All right, I want you to look at this triangle. Do you see this triangle that I just highlighted in yellow? So you're going to look at the side that has an expression and a side length and set them equal to each other. So what's our equation to solve for x? Good. X root 3 equals 30. All right. Annalena, solve this for me. What should I do? We got to solve for x. Good. We're going to divide by root 3 on both sides. Will, can I leave it like this? No. What do I need to do now? Good. We need to multiply top and bottom by root 3. So we get 30 root 3 over 3. What now, Mia? Good. Now we're going to simplify this down to 10 root 3. That means BD is 10 root 3 and BC is 2 times 10 root 3. What's 2 times 10 root 3? 20 root 3. Now go back to what it was asking. Find the distance from the chord to the center. Which one of these represents the distance from the chord to the center? The 10 root 3. So we are 10 root 3 units. All right, this is your homework for section 10.1. Now let's go on to 10.2. Okay, a bunch of theorems. I decided that I'm not going to do any proofs in chapter 10, so all these theorems will just really be applied to algebra problems. Okay, all the theorems will be applied to algebra problems. If two chords are equidistant from the center of a circle, then they are congruent. All right, so I've now introduced a new word here. I've introduced the word equidistant. Equidistant, exactly what you think it means, an equal distance. So they're saying if two chords are an equal distance from the center. So question 1, how do we determine the distance from a chord to the center? It's the length of what? The distance from a chord to the center is the length of what? We've just done this 5 times already. The distance from the chord to the center is the length of what? Ishita, what is it? The distance from the chord to the center. Good. It is the length of the perpendicular. The distance from the chord to the center is the perpendicular. So they're saying if two chords are an equal distance to the center, meaning if their perpendiculars are the same length. So let's say we have PX and PY. If they're congruent, then if the two chords are an equal distance from the center of circle, then they are congruent. So if their perpendiculars are congruent, then their chords are congruent. And I'll write that out for you. If perpendiculars congruent, then chords congruent. That's what this means. If the perpendiculars from the center of the circle are congruent, then the chords are congruent, that they intersect. All right, now we're reversing this. Now they're saying if the two chords of a circle are congruent, then they are equidistant from the center. So now they're saying, well, let's say I told you CD and AB, the two chords are congruent. What can we conclude? We can conclude their perpendiculars from the segment, from the center, also have to be congruent. So if chords are congruent, perpendiculars from center are congruent. Also here too, if perpendiculars, it should have been from center congruent. There we go. Perpendiculars from center congruent, then chords congruent. Chords congruent, then perpendiculars from center are congruent. All right, do we want to see how this would show up in problems? Are we still writing? I'll give you a second to finish writing. Okay, let's look at number 1. So here we have circle O, so we know the center of our circle is O. Now we're being told that AB is congruent to CD. Michael, AB and CD are what in reference to our circle? What are they called?
They are the chords.
They are the chords. Since they're the chords, Navia, since the chords are congruent, what else can we say are congruent? You got it. Then we can say the perpendiculars PO and QO are congruent. So if the chords are congruent, the perpendiculars from the center are congruent. If the perpendiculars from the center are congruent, then the chords are congruent. Then we're going to have that OP, I'm going to label it, is 12x minus 5, and OQ is 4x plus 19. We want to find OP. In order to find OP, I need to solve for x. Well, aren't OP and OQ congruent? So can I set their variable expressions equal to each other? Yeah, so we're going to say OP is congruent to OQ. Or whatever. So we're going to say 12x minus 5 is equal to 4x plus 19. Now we solve. So I'm going to subtract 4x on both sides. And we're going to have 8x minus 5 is equal to 19. We're going to add the 5 on both sides, so 8x equals 24, so x will equal 3. I wasn't asking for x. What was I asking for? Yes, OP. So now we're going to say, well, OP was 12x minus 5. So OP will equal 12 times 3 minus 5. So we get 36 minus 5, which is 31 units long. All right, you guys try number 3. All right, what should you have done here? So here they're telling us that PQ and PR are congruent. So if the perpendiculars from the center are congruent, you need to conclude that the chords are congruent. And then we have that AB is 6x plus 14 and CD is 4 minus 4x. We want to find AB. Well, aren't AB and CD congruent to each other? So we're going to say, well, AB is congruent to CD. So therefore, 6x plus 14 is equal to 4 minus 4x. Add that 4x over, we have 10x, subtract the 14, equals negative 10. So x equals negative 1. Is it okay to have a negative x value? Absolutely. What's not okay? You're allowed to have a negative x. What's not okay, AJ? Good, if when you plug in the sides or angles are negative. So now we want to find AB. So when I plug in for AB, I get 6 times negative 1 plus 14. So we get negative 6 plus 14, which is 8. And that is absolutely perfectly fine. All right, how many people got that correct? Good. So y'all are paying attention. All right. You know what? We're going to take out number 4 because I said we're not going to do any proofs in this unit. We're going to do a problem that's a little bit trickier. Could you hold off until we finish and then go? Yeah. Okay, I want to do independent number 1 with you. So here we have circle P, so that means P is the center of the circle. They're telling us that PQ is congruent to PR. Those are the perpendiculars from the center. If the perpendiculars from the center are congruent, Christine, what else can I say are congruent? Good, the chords are congruent. They're telling us that AB is represented by x squared plus 10x. Now be very careful. I am not saying CD is 2x plus 10. Not CD. CR is 2x plus 10. Oh, sorry, 2x plus 20. Thank you. Biggest mistake. Biggest mistakes. Kids want to be robots, so they just say x squared plus 10x equals 2x plus 20. Is that correct? No, because the 2x plus 20 is just part of it. It's not the full CD. So now we have to remember one of the theorems from 10.1. It said if a radius, a segment from the center, if a segment from the center is perpendicular, doesn't it bisect it? So if CR is 2x plus 20, then RD is also 2x plus 20. So now we know AB is congruent to CD. So what does that mean? X squared plus 10x is equal to what? Jeff, what is it equal to? X squared plus 10x is equal to what?
Oh, 4x is 40.
You got it. 2x plus 20 plus another 2x plus 20, which equals 4x plus 40. Can someone tell me, how do I know I need to factor this problem? How do I know? Dimitri? Because of the x squared. Now, in order to factor, don't I need to set it equal to 0? So I'm going to subtract the 4x and I'm going to subtract the 40. So now we're going to have x squared plus 6x minus 40 equals 0. So I need two numbers that multiply to negative 40 but add to a positive 6. What are my factors of negative 40 that add to a positive 6? Well, you got it, 10 and negative 4. Are my answers 10 and negative 4 for x? No, we got to set them equal to 0 and solve. X plus 10 equals 0, x minus 4 equals 0, x equals negative 10, x equals 4. We are allowed to have a negative x. We're not allowed to have a negative side length. So when I plug in that negative 10, 2 times negative 10 is negative 20. Negative 20 plus 20, isn't that 0? Can I have a length that's 0 units long? No. So we can't have a negative length, and we also can't have a 0 length. So I am rejecting the negative 10. So that leaves us with 4. So now I'm going to plug in 2 times 4 plus 20. That's 28 plus another 28. So how long is CD? Yeah. 56 units long. All right, your homework is listed here. I will also put it on Google Classroom. We are done for today.